Okay, in this video we're going to look at reaction classes. Our goal is to be able to classify reactions based on mechanism. So classifying reactions is always going to depend on recognizing the change in the structure going from the reactants to the product. So what's changing in the molecule, and then that will tell you what the reaction type is. So you have to study the structures of the starting material and the products and see how they're changing. Let's look at a simple example first of carboxylic acid derivatives, which are quite common in biochemistry. So carboxylic acids themselves have a carbon with a double bond to an oxygen. That's a carbonyl group. And then another oxygen and hydrogen. So we have this carboxylate functionality. Now, if we substitute the hydroxyl here with various groups, like an alcohol, we could get an ester. Or if we change that into a thiol, we would have a thioester. Or with an amine, now we would have an amide. Okay, so these are all considered different derivatives of carboxylic acids. Now, when we have a derivative of carboxylic acid, that can be converted back into a carboxylic acid through a hydrolysis reaction. In other words, if we imagine replacing each of these different groups here, an alcohol from the ester, the thioester, or the amide, with simple water to go back to the carboxylic acid, now we have the hydroxyl here, we're back to a carboxylic acid. So the hydrolysis reaction is a way to convert various carboxylic acid derivatives back to a carboxylic acid. We can look here at an example of an ester, and the mechanism of the hydrolysis is shown here so you can see that in detail. So we would have a hydroxide ion, for example, attack a carboxylic acid derivative. This is a methyl ester, so it's the ester formed by methanol in green condensed with a carboxylic acid here. So we have a methyl ester. Now when the hydroxide ion attacks, it attacks the electrophilic carbon here. We push the electrons onto the oxygen. We get this intermediate where we have 4 groups attached to this carbon, so it's a tetrahedral structure because these 4 groups try to get as far away from each other as they can, and that makes a tetrahedron or a tetrahedral geometry. And then the electron density on the oxygen comes back down and reforms this carbonyl. And now, instead of kicking out the alcohol, the hydroxyl group, which was the attacking nucleophile here, we kick out the alcohol, the methanol. And so the methanol, the alkoxide, methoxide here is the leaving group. And we're left now with this carboxylic acid, and it's protonated. So if we deprotonate, we have the carboxylate form, the deprotonated form. So in this case, we see how we're doing a hydrolysis reaction. We're converting an ester to a carboxylic acid. If you were just given the ester and the carboxylic acid and methanol and asked what reaction type is this, you would say, oh, this is a hydrolysis reaction, because you recognize you're going from the ester to the acid. Now, carboxylic acid derivatives have different levels of reactivity. So the less reactive ones are amide, for example. Ester is a little more reactive, but still fairly unreactive overall. A thioester is quite reactive, one almost to the degree of being unstable. It's readily hydrolyzed by water. Anhydride or phosphoanhydride, these kind of structures are all similar, are also high in energy, or in other words, are very reactive to hydrolysis. So let's look at hydrolysis of an amide. Amides are interesting, of course, to us because amides are peptide bonds. That's the type of bond found between amino acids in proteins. So amino acids are connected to each other in the form of these amide bonds in amino acids, where the amine group of one amino acid is condensed into an amide bond with the carboxylate carbonyl of the next amino acid. Okay, so this is the amide bond. And if we wanted to see the hydrolysis of an amide bond, that would involve attack of water, so it's hydrolysis, on the amide carbonyl. The electron density goes onto the oxygen, and we have, again, this tetrahedral intermediate. Electron density comes back down. Now the leaving group is the nitrogen, the amino group. That is, the electrons flow onto the nitrogen, they get protonated, and we end up cleaving that amide bond. So we've broken the carbon-nitrogen bond. Now we have the free carboxylate, and we have the amino group. So if we zero in, again, this is the amide bond, these three atoms here, and then now in the product we see the carboxylate has been formed. We've replaced the nitrogen with an oxygen, and then the amino group has been separated. So now we have just the free amine. So that's a hydrolysis of an amide, or of a peptide bond. Now this is a very important reaction in biochemistry because it's catalyzed by a key group of enzymes called proteases. So those are enzymes that specifically catalyze this hydrolysis reaction, cleaving a particular peptide bond or amide bond within a protein structure. So they will recognize the amino acids around this amide bond and only cleave one or a few of the amides within a long protein. So the enzymes such as proteases catalyze this hydrolysis reaction. Another example of the importance of hydrolysis reactions is in ATP. So ATP, we have discussed, is an energy store. It's an energy currency. It's used to power many reactions, and that's through the hydrolysis of ATP. So ATP is a phosphoanhydride. This is the very reactive structure to hydrolysis that I mentioned before. And so we can have water come in here and cleave this phosphoanhydride bond, and then we get ADP, which is the rest of the molecule here, and then the inorganic phosphate over here. So it's the hydrolysis of this phosphoanhydride bond, these 5 atoms here, that is liberates energy that's used to power other reactions. So ATP hydrolysis, another important example of hydrolysis in biochemistry. So let's step through glycolysis, which we'll be talking about in class, and look at some examples of reaction types to give you some concrete examples. So if we begin with the phosphorylation of glucose, this first step of glycolysis, is catalyzed by hexokinase, uses ATP, it transfers a phosphate group onto this alcohol of glucose. So we get glucose 6-phosphate. Here's the 6 carbon. The glucose has now got this phosphate group on it. That's the terminal phosphate we saw in the last slide here from ATP has now been, actually in this case, it's not a hydrolysis, it's a group transfer. So the phosphate group has been transferred from ATP onto that 6th position of glucose. So that's glucose 6-phosphate. That's a group transfer reaction. That's where we take a piece of ATP or some molecule and we transfer it onto another molecule. So that's one type of reaction. Another important one is shown in the next step in glycolysis, catalyzed by phosphoglucose isomerase. So the name kind of gives away the kind of reaction here. But if we just look at the structure, we can use that guideline, look at the structure, see what's changing. So we see we're going from, in this case, glucose 6-phosphate to fructose 6-phosphate. Now these are drawn in the cyclic forms, But if I draw them out here, I have them in the linear forms. So in the linear form, we've just removed the ring. So we've just opened up the molecule so we can see where the carbonyl is. In glucose 6-phosphate, the carbonyl is on the terminal carbon. So that makes it an aldehyde. An aldehyde has a carbonyl on the terminal carbon. Fructose 6-phosphate has the carbonyl on the carbon next to the terminal carbon. So that makes it a ketone because the carbonyl is substituted with 2 carbons. Now it's a ketone. This is an aldehyde in the case of glucose. So basically, when we go from glucose to fructose, we're going from an aldehyde to a ketone. And actually, everything else is the same. We're just migrating the position of this carbonyl from the terminal carbon to the second carbon, and now the terminal carbon in fructose becomes an alcohol. So it's all the same atoms, they're just arranged in a slightly different way, which makes it an isomer. So glucose 6-phosphate and fructose 6-phosphate are isomers. So this is an isomerization reaction. So that's a very important class of reactions in biochemistry where we have an isomerization. We're moving between 2 different isomers. In other words, the same set of atoms, they're just arranged differently, connected differently. And so a classic example is this type where we're isomerizing an aldehyde to a ketone or a ketone to an aldehyde. In other words, we're just, in this case, moving the position of the carbonyl, exchanging the position of the carbonyl and the alcohol on these 2 carbons. Okay, so that's an isomerization reaction. We can look, then there's another phosphorylation reaction here, so that's a group transfer, just like the first one we saw. Now, the next reaction, going from fructose 1,6-bisphosphate down to glyceraldehyde 3-phosphate, that's catalyzed by aldolase. So again, the name gives it away. That's a so-called retroaldol reaction. It's the opposite direction of a normal aldol reaction, you may remember from organic chemistry. In this case, we're taking a 6-carbon molecule and breaking it down into 2 3-carbon molecules. We get dihydroxyacetone phosphate and glyceraldehyde 3-phosphate. They both have 3 carbons. And that makes it a carbon-carbon bond cleaving reaction. That's a type of reaction, and more specifically, a retroaldol reaction. So you'll periodically come across retroaldol reactions in biochemistry. And the way you can recognize that is it's a carbon-carbon bond cleaving reaction. And we'll go through the mechanism in class and you'll be able to recognize it more specifically. But that's a clue because we're breaking 6 carbons down into 3 carbons. That means it's going to be some type of carbon-carbon bond cleaving reaction. Now, when we consider this step here, the 2 products of the retroaldol, dihydroxyacetone phosphate and glyceraldehyde 3-phosphate, have to be isomerized. In other words, DHAP here is isomerized or converted into glyceraldehyde 3-phosphate. So what kind of reaction is that? Well, again, the name of the enzyme gives us a clue, triose phosphate isomerase. It's an isomerase because, why? We're going from the ketone here to an aldehyde. Again, it's just like the glucose to fructose isomerization. We're isomerizing between a ketone and an aldehyde, and we can go both ways, of course, aldehyde to ketone. So those are 2 isomers, and the enzyme is isomerizing, or it's converting between those 2 isomers, just exchanging the carbonyl with the alcohol as we go between the ketone and the aldehyde. So that's another example of an isomerization reaction. And that, again, is catalyzed by triose phosphate isomerase. And again, the clue is in the name. A triose is a 3-carbon sugar. So this is glyceraldehyde is a 3-carbon sugar, so it's a triose. It's got a phosphate on the end because it's glyceraldehyde 3-phosphate. So it's a triose phosphate isomerase. It isomerizes between that triose phosphate and dihydroxyacetone phosphate. Now what about if we continue to step through glycolysis? Jumping down a bit, we see 3-phosphoglycerate and 2-phosphoglycerate. What kind of reaction is that? So think about that. We've got all the same atoms. The phosphate group here is moving from the 3-carbon to the 2-carbon. So nothing else is changing, so you should guess it's an isomerization because these are isomers. Same atoms, just connected differently. We're just moving this phosphate group over. That's an isomerization. And the enzyme that does that, it's not called an isomerase. In this case, it's called a mutase, but it's the same effect. It's moving the phosphate group from the 3 position to the 2 position. Phosphoglycerate mutase. That's phosphoglycerate is the substrate. Mutase is moving that phosphate group over from the 3 position to the 2 position. And it's another kind of isomerization reaction. Okay, now what about one more example? 2-phosphoglycerate now, stepping down here at the bottom, 2-phosphoglycerate to phosphoenol pyruvate. So what's changing here? Again, we have to look carefully at the structure. The carboxylate is here, okay, so that's not changing. It often helps to map the atoms one on the other and see what's different. So this carbon is this carbon in the middle, the 2-carbon, so that's still there. It's not, it's drawn slightly differently, but it's still there. The 3-carbon is here also, so that carbon is not changed, that's still there. The O-phosphate, the phosphate group is still there, so that's not changed. So what's different? Well, it looks like the only thing that's different is we've lost one hydrogen, proton actually, because now we have a double bond, and we've lost this hydroxyl group because we've just got the 2 hydrogens on this carbon. The hydroxyl group is gone. So net, we've lost H-OH, and we've introduced a double bond. What is it called when we lose HOH? Well, what is HOH? HOH is water. So we've eliminated a water molecule here. So what happens when you're exercising, you're running, you're not drinking enough, you don't have enough water, you get dehydrated, right? So this is a dehydration reaction. It's catalyzed by enolase because you're making an enol type structure. Enol, it's got the phosphate on there, but it's an enol type structure. So it's enolase, and it's a dehydration reaction. It's removing the elements of water from this molecule. Okay, so to summarize, in this video, we learned about hydrolysis reactions. It's a common reaction type in biochemistry, so that's one you want to be able to recognize. We've seen that carboxylic acid derivatives have different levels of reactivity, but even the unreactive ones, like the amides, peptide bonds, can undergo hydrolysis in the presence of an enzyme that facilitates that, like a protease. And then we saw some examples of these other reaction types in glycolysis. So the key is looking carefully at the structure and seeing what's changing, and then figure out, based on that, what kind of reaction it is.